we start with the image formation by a convex lens. Okay, or simply we can say how to get the images when the object is placed at various places on the principal axis. Okay, students, here we do the image formation by a convex lens. Then after, we talk about the image formation by a concave. You are aware of the lens, students, as I told you. Okay, we discussed a lot about that. As you know that it is a biconvex lens. Okay, there's a representation of it in this way. We are recalling back the concept, students. These two are the refracting surface. Listen, these two are the refracting surface. And you will learn that first we have to locate the optic center, students. And you know that optic center is the point through which the light passes without any deviation. Just I am showing here. It falls like this, get refracted, and it passes, and then it come out from the other surface. If you join these things, it doesn't get deviated. Okay, students, the next primary thing what you have to know is locating when the lens is very thin. When the lens is very thin, and you can symbolically represent a lens like this. It is a symbolic representation of thin concave. It is a thin concave lens. If you draw convex lens, symbolic representation would be like this. Okay, arrowheads are down and the tails of the arrows are upside. Okay, we call them as the concave and as well as the convex, students. I hope you are getting my words. Okay, students, these are the symbolic representations. Those are biconcave and as well as the convex. Now, say, students, we are going to draw the images which are formed by a convex lens. Here I am taking a thin convex lens. Let's take thin convex lens, students, and say it has the principal axis. Okay, students, and obviously it is the optic center. Okay, students, now I am taking an object, and you know that objects are two types. One is the extended object, and second is the point size object. Here I am taking an extended object. I am locating the focus, and as well as it is the first refracting surface, and we call it as the C1. And as well as we have the F2 here. It is our notation, and automatically it could be F1 and say it as C2. You can take any notation, students. Here, if you watch it carefully, this object is kept beyond the center of derivation. Okay, students, to draw the image, we need at least two light rays, students. Okay, one has to pass parallel to the principal axis, and one should pass the optic center. As you know that the ray which passes through the optic center doesn't get deviated. Okay, this ray get refracted and it passes to the focus. And the two will meet at a particular point. Okay, students? There's somewhere we have the C2, that is C1, and we get the image here. If you say it is the object OJ, okay, students, and we are calling the image as IG. It is the image which is IG. OJ is the object. Okay, I am showing, as you know that it doesn't deviate, but it's parallel to the principal axis. Always get refracted and it's passing through the focus. You see, remember this thing to make the diagram very easy. What you have to remember, whenever you are moving towards the lens, the image will move away from you. I put the object more than of curvature. It is far away from the lens. The image near to the lens. That's why this distance, call it as the V, image distance, and here it is U. Okay, U is greater than V, students. All the time. If you see, the object is kept beyond the center of curvature, U is greater than V. And see, if you watch the image, see the arrowhead. The arrowhead appears to be upside down. See this. Here it is upside down, and here it is. It means inverted one. We call it as the inverted, upside down. And the object is erect. Okay, students. When the object is erect, the image is inverted. Are you watching this object? And this one can be taken on the screen, students. This image can be taken on the screen. That's why we call it as the real image. And what about the size? You know that magnification can be had as less, that is, okay, students, here we kept beyond, okay, students, C2, and we found the image here. What is the characteristic of the image? See this? I told you it is the real, can be taken on the screen, and the head is upside down, and it is what? Inverted, and magnification is less than 1. Means what? It is smaller in size, or simply you can say diminution, very small when compared to the object. Here it is the image characteristic, students. When the object is kept in this way. Okay, students, the image is inverted. I hope you understood how the image will be formed when the object kept beyond C2. Let's do one more. We are moving towards the lens, students, here. Let's see the next diagram. We will see what would be fine. Okay. See this? It's the same principal axis, and we have the same lens. That too, it is the convex. See, gradually we are moving towards the center of curvature. Okay, students, now it's the center of curvature. You say it is C2. Here I am keeping an object. It's the object which is kept. Okay, students. Then we got C1, take the focus. Then to draw the diagram, what we have to do, it is the optic center. From the head of the object, we have to take one ray. It has to move without any deviation. It passes in this way. And another ray you have to take. it is parallel to the principal axis. Okay, students. Then after this ray gets refracted, that means actually it changes its path and it passes through the focus. We named it as the F2. Maybe in your textbook you will find it as the F1. Nothing to worry. It is a just sign convention. Okay, students. Here, the same thing is applied here. See this? We are reaching towards the lens. The image is moving towards us. The gap is decreasing. Let's say it is object distance and it is the image distance, students. And you know that magnification, m is equal to v by u. Here, u is equal to v since the distance of first center of curvature and second center of curvature are same. Okay, then it is equal to 1. Means what we will write? Of same size. Of same size. There is no magnification. And the same thing we have to apply here. It is heads. It is the top head. It is OG. And it is IG. Okay, inverted. And third one, it is real. Okay, students. Okay, it is of same size, inverted and real. Okay, in this way, you can find out the image position. Okay, students. Let's see one more case. I hope you understood the second case. And we are going with the third. Here I am doing. Now what I am doing here? See this? This time I am taking same. Let's. Okay, students. Okay. In the center of curvature we said. And some way we have the focus. And I kept an object here. OJ is the object. Let's see what will happen. You know that one ray has to pass parallel to the principal axis. And one ray through the optic center. Okay, students. Okay. Then what happens here? After refraction, it passes. And if you join, it is the image we form. It is image ZG. Okay, we have to find out the location of the image. It is the object distance students and it is the image distance v. Okay, see here students, when we are away from the center of curvature, then image is what is that form in between the focus and as well as the center of curvature. Here in this case, what happens? If you go near to that, then what's happening? Here the image will move away. Okay, you will find the C1 here and as well as the F2. Okay, here beyond the C1, image will be formed beyond C1. Same characteristic it has. It is a real image and it is inverted. Here V is greater than U and magnification is the ratio. It is equal to greater than 1 students. Okay, means what we can write? It is enlarged. It is the enlarged image students. Okay, students, let's say one more case. We'll say then after we are going further, students. Let's see what could happen to the image. Okay, this is the same principal axis. Actually, we have to draw the lens first. Later, we have to locate the principal axis. This is the optic center, and it is the first focus, students. Here, I am keeping an object. The object is kept here, and I have learned that how the image will form. We have to take, and we should pass through the optic center straight from the head, and we call it as OJ. It is the second focus. Here in this case, the final image which is formed is an enlarged one, but we can't define what size it has. Okay, here maybe the vect at infinity, but we can't define where would be the image position. Okay, students, just you think that you kept your eye here, then we can. But actually, that condition is not applied for your examinations. That's why we can't identify where would be the image, maybe it is infinity, and what are the characteristics of the image. This is one case, students. And finally, and the important case we are discussing now. Okay, students, we have to take a biconvex lens, and we have to locate the optic center. Then it might be the principal axis, and you know that it is F1, and here we will find the C1. Somewhere we get the F2. Right now, and it is the optic center. Here I am keeping the object. It is OJ. Let's see what could happen. Obviously, one ray has to be taken parallel to the principal axis, and one ray have to move through the what? Pass, and we get here the center of curvature. Okay, students. Then these are the rays. If you watch the rays, they appears to be, what's that, going away from each other. That means the gap has been increasing. You can't, what's that, make them to meet in this direction. That's why we are doing. We are producing them back. There we will find the image somewhere. Okay, students. Here it is the image. It's the image. Okay. It is a special. With the concave is, what's that? Wherever you keep the object in front of the lens, the final image would be, and you know that a concave can be represented in this way. It is a concave. Okay, students. Here, same. Okay, anywhere you can keep the object. The object here. It is the object which is kept here. One ray is proceeding in this way. As you know that a concave is the diverging lens, the ray might pass in this way, it get diverged. If I extend it back, it is appearing to be was that intersecting the principal axis at a point, and we call it as the focus. And you know, students, where we will find the image. Okay, students, if you watch it carefully, it is the erect image, okay, and it is the virtual, and also its magnification is less than 1. Wherever you keep the object, finally you will get, wherever you keep the object, you will find the image in between the optic center and as well as the focus. Yes. Image positions by keeping the object at places on principal axis. Students, it is the one of the important questions for your examination. Okay, students, let's do the lens formula. Here, often we mistook that lens formula and as well as the lens maker formula are same. Lens formula and lens maker formula are same, but the two are different. Okay, to know about the lens maker formula, you can visit my YouTube channel and you have a video on the lens maker formula. Lens formula is different. Lens formula gives us the relation between the image distance and as well as the object distance. And as well as the object distance with respect to focal length. Himavarsha, good evening. I am getting plenty of messages. Right now my students are joining. Okay, I saw your name, Himavarsha. Welcome to the channel and listen. Okay, we are finding the relation between, okay, focal length of a lens. The second is object distance. And third is the image distance, students. Okay, we have to find out the relation between these three. Okay, students. Okay, generally focal length, you know that it is shown with the letter F and is the U and it is the B. Okay, we are deriving an equation for the relation between these three. That is what we reciprocal for lens formula for real object and as well as the real image. Here, what I am writing here, lens formula for what? Real object and real image. Okay, students. Okay, it's a real object and real image. And you know that what is the real object is? The object which appears, which shows us the rays are diverging from it. It is the real, and where the rays are converging, it is the real image. Okay, you have to take a thin convex lens, students. Here, lens formula. In case of convex lens, it is convex lens formula. Write it. First of all, you have to take a lens, students. Follow this class with attention. Maybe you have a chance to get a problem from What is the principal axis? It's the imaginary line which is passing through the optic center, joining the two center of curvatures. Okay, students. Here, I'm locating the focus and as well as the center of curvature. Let's say it is C2. Okay, there is no need to locating also. You can solve this. Here I am taking an object. Okay, students. I am taking an extended object here. Say it is the object. Okay, students. I am naming it as OJ. Listen my words carefully. You know that the rules to draw the image. Here, one ray has to pass parallel to the principal axis. I am making a ray to pass like this. It's going parallel to the principal axis. Okay, students. The next one, we have to take it to pass through the optic center. It's the second ray. Okay, this ray passes without any deviation, you know that. And this ray gets refracted, that means changes its path. And it passes through the second focus it is. And the two light rays will intersect at a particular point. There we would find the image. It is the image position. Okay, students. Okay, it is the object, extended object. I am calling it as AB. Okay, and the image we form, I am naming it as A dash and B dash. It is the O and the focus. Okay, students, let's locate the object distance. Say the object distance is U. That means from optic center to the object, we call it as the object distance. And from here to here, it is the image distance, students. We have the object distance and the image distance. What is the focus is? It's between optic center to second focus, and we can show it like this. It is the focus. Okay, students. If you watch it carefully, here I am making that a little easier. Actually, this lens is made of two plano-convex lenses. Okay, of same radius of curvature. However, are different radius of curvatures. Okay, students, it is the V. And see, if you watch it carefully, you would find I am calling it as the O and I am locating this point here. And if you watch, I am doing, see the lines what I am drawing here. I am drawing with green pen. Maybe they are visible to you. Let's see. I am extending this part. Okay? If you watch them closely, okay, students, we have the two triangles here. The two similar triangles. That is OAB and as well as the OA dash B dash. Okay, students. Triangles O AB and O A dash B dash are similar. And you know that when the two triangles are similar, their corresponding side ratios are same. It is OAB and as well as the O, okay, B dash A dash are the similar triangles. Their corresponding side ratios are same, students. Here I am taking the ratios of these two. I can write it as AB by A dash B dash is equal to AB by A dash B dash. And I have to take the basis series is equal to OB by OB dash. Okay, students. OB by OB dash. See this, what is OB? OB is equal to U. OB is U and OB dash is equal to V. U by V. I can write it as AB by A dash B dash is equal to what? It is U by V. I am freezing this point. AB by A dash B dash is equal to U by V. Are you getting me, students? Say I am showing it again. Here see. Here's one triangle and I had one more. These two triangles are similar. That's why their corresponding side ratios are same. AB by A dash B dash is equal to OB by OB dash. I took the values and I put the values. It is AB by A dash, B dash by U by V. I am not taking any sign convention. Okay, this set of triangles are okay, students. Then after, we can find out one more set of the triangles. See this triangle, students. And I had this. Okay, students. Okay, see the dot lines. They are horizontal. See, these are. They are also the similar triangle, students. Triangles okay, F2, MO and F2, B dash and A dash are similar. And you know that when the two triangles are similar, their corresponding side ratios are same. Okay, students, their corresponding side ratios must be same. Here we can write OM by A dash B dash. OM by A dash B dash, okay, is equal to OF2 by okay, F2 B dash or B dash F2. Getting me, students? OM by A dash B dash is equal to OF2 by F2 B dash. Okay, students? So this, but here, if you watch it carefully, OM is equal to AB. I am replacing OM with AB. OM with AB. And we will get, it is AB by A dash B dash is equal to OF2 by B dash F2. Okay, students? Here you know that OF2 is equal to focal length F, but we don't know the value of the F to be. Then we can find it as like this. The total distance is V and it is F. Then it could be written as V minus F. Getting me, students? It is the distance V and from here to here it is F. The remaining this distance is equal to okay, V minus F. I am putting that value. B dash F2 as V minus F. Okay, then this can be written as AB by A dash B dash is equal to OF2. F by V minus F is the second equation what we require. Okay? It is AB by A dash B dash is equal to F by V minus S. Here AB by A dash B dash is equal to U by V. We are comparing the two. Okay, we can write it as U by V is equal to F by V minus F. Okay, students, we are doing cross multiplication. U of V minus F is equal to V of students. And you can write it as UV minus UF is equal to VF. Okay, we have a relation, students. UV minus UF is equal to VF. Dividing, okay, the entire equation with UVF. Let's see what happens. We are dividing with UVF. It is UV by UVF minus UF by UVF is equal to VF by UVF. Okay, students, let's cancel U and VV here, and we get this 1 by F minus UB cancel with the U, and F get cancels with F, and we had it as 1 by V. And see this, V is cancelled with the V, and F is cancelled with F. We had 1 by U. Okay, we had it as 1 by U. Okay, this is 1 by F is equal to 1 by V plus 1 by U. But we wrote the equation as 1 by F is equal to 1 by V minus 1 by U, students. Let's put the sign convention. It is the focal length. If you follow, focal length is positive since it is along the direction with the incident rays, and V is also positive. Okay, and see, U is measured against the incident ray, that is, U is negative. Then we can write it as 1 by F is equal to 1 by V minus 1 by U. It is the desired relation, students. It is the relation to find out the focal length of the lens. Please note it, students.